Hello everyone, my name is Arosina and in this video we will be talking about the field effect transistors which are commonly known as the FETs with a focus on the junction field effect transistors or the JFETs. These are one of the most important parts of the modern electronics which are used in devices like the amplifiers and digital circuits. Let us take a closer look at how they work and why they matter. The field effect transistors or the FETs are the core components in many of the devices which we use every day, ranging from the smartphones to the smartwatches to the computers. They play a key role in making the electronics faster, more efficient and more reliable. In this video, we will cover the different types of the field effect transistors, their working principle, their advantages and their applications, and we will dive deep into these concepts to get a thorough understanding of what are field effect transistors. But before that, let us take a brief look on what actually are transistors. A transistor is a small and basic electronic component which is connected into a circuit and allows the flow of current. It serves two main functions, amplifying the weak input signal into the stronger output signal and acting as a switch. You can think of it like a gate. When the gate is opened, the current flows through and it passes through. The signal is amplified, making it stronger as it enters and as it exits. The transistor has a lot of real-world applications. They are used in EVs, they are also used in the smartphones we use every day, every time, and there are countless other applications of the transistors. There are mainly two types of transistors, the bipolar junction transistors and the field effect transistors. And the main highlight of this video is the field effect transistor, or say the junction field effect transistor. So let us take a look at what the field effect transistor actually is. Field effect transistors or the FETs are key components in modern electronics. They are used to control the flow of current in various devices, from smartphones to computers. FETs are known for their efficiency and small size, making them ideal for a wide range of applications. In this slide, we can see different types of FETs that serve as various functions in the electronic circuit. Now let us take a closer look at the theoretical definitions of the FET. A field effect transistor or the FET controls the flow of electrical current using an electric field. It works by adjusting the conductivity of the semiconductor channel between the two terminals, like commonly known as the source or the drain, and with a voltage applied to the gate. FETs are widely used for amplification and switching in the electronic circuit. They are very essential in the modern electronics and they are found in different devices such as the computers or the smartphones, different audio equipments and the power management systems. A FET is a voltage control device, which means on varying the input voltage, we can tweak the output currents. Apart from this, FET is a unipolar device, which means the current flows due to the contribution of only majority charge carrier, and the majority charge carrier might be electrons or holes depending on the configuration of the FET. There are mainly two types of FETs, the junction field effect transistors or the JFETs, or the metal oxide semiconductor field effect transistor, commonly known as the MOSFET. Our main agenda is to discuss the JFET. The JFET is a three-terminal transistor which controls the flow of current through a semiconductor channel using a biased PN junction as a gate. They have very high input impedance and low noise performance which makes them very suitable for the industry use. JFETs can be further classified into two types, the N-channel JFET and the P-channel JFET. Here we can see the symbol for both N-channel and P-channel JFET. It is worth noting that in the N-channel JFET, the arrow points toward the gate, and in the P-channel, the arrow points away from the gate, showing the direction of current. Now let us take a closer look at these terminals one by one. The gate controls the flow of current between the source and the drain. A voltage is applied to the gate, which creates an electric field that regulates the current. The source is the terminal where the current enters the FET. It supplies the charge carriers that flow through the semiconductor channel. The drain is the terminal where the current exits the FET. It collects the charge carriers after they pass through the channel. So now let us look at the working of an N-channel JFET. If we look very closely to the biased circuit, we can notice that the drain and the source terminals are connected with the N-channel. We can also observe that the gate is connected to the P-type semiconductor and there is a formation of a reverse biased PN junction. When the biasing is applied, we can see that PN junctions forms at the interaction areas of the N and the P semiconductors. Between the two semiconductors, there is some free space left. In that free space, the electron travels from the source to the drain, which results in the current called the drain current to flow from the drain to the source. When the gate source voltage is kept zero and the drain to the source voltage is increased, the drain current ID increases linearly in a linear region. At one point, it reaches the pinch-off point, and after that, it enters a saturated region. Again, if we keep on increasing the VDS very further, at one point the system even breaks down. Here we can see the transfer characteristic of the N-channel JFET. We can see different operating regions. Now let us look at the gate source voltage and how it affects the output current. This will also clear why the JFET is called a voltage control device. When we provide more negative VGS, the width of the depletion region increases. As the width increases, which means that there is less path for the current to travel and hence the value of the drain current decreases. So in this way, by changing the input voltage, we can vary the output current. Similarly, let us look at the P-channel JFET. Again, as we observe in the N-channel JFET, we can see that the drain and the source is connected to the P-type semiconductor and the gate is connected to the N-type semiconductor. There is also a formation of a reverse bias PN junction at the gate. This time on applying the bias in voltage, not the electrons but the holes flow from the source to the drain. Therefore, the drain current flows from the drain to the source. Also, we can see similar characteristics on varying the gate to the source voltage. So here we conclude the working of the JFET, and let us now move on to the advantages of the JFET. There are different advantages of JFET which make it optimal to use and an industry standard. Some of the advantages include high input impedance, low noise operation, low power consumption, good thermal stability, and simple construction. The JFET has lots and lots of applications. Some applications in the electronics area and the electronics industry are that the JFETs can be used as low noise amplifiers, analog switches, voltage control resistors, impedance buffering, and switching circuit in logic gates. So here we conclude our today's discussion.